Thank you all for being here. We're going to do a little bit of a fireside chat about what's the exciting things happening in the compute over data space, some of the things that make Filecoin an awesome home for many different compute over data networks to grow and thrive and utilize some components there, and then advice for all of the amazing builders and developers in the audience who are building compute over data networks that can be, harnessed to go and make many of these successful and collaborative. And so that's the agenda. We might plug in and present some stuff every now and then when we have a diagram or image that's worth 1,000 words. But maybe intros, probably good. My name is Molly Mackinlay. I lead the PL engineering and research team.
Hi, my name is Juan. I started PL.
And Filecoin and IPFS and a couple other things. Cool. Well, maybe I'll just kick it off today, starting with the compute over data space. As someone who's been kind of like pioneering in Web3 infrastructure for a long time, what are some of the most exciting developments that you see happening with compute over data today? What are some of the things that get you the most excited?
Yeah, so we first started talking about compute over data probably, I think, 2 years ago when we started shifting to layering computation on top of IPFS networks and in particular the Filecoin network. Just for everybody, maybe a show of hands. How familiar are people with Filecoin in general here, just so I get a sense of, like about half, cool. So the way you can think of Filecoin is that it's a large subnet of the IPFS network. So if IPFS is mapping to HTTP and it's a different way of moving around data, Filecoin is kind of like S3 or Glacier and providing a data storage service that you can hire. So it's a very large storage provider or like network of storage providers in the IPFS network. And a key goal in designing systems like IPFS and Filecoin was to enable a computational platform that enables people to run their all their kinds of jobs and so on that they might want to do on top of the data, right? So data has gravity. Once there is a lot of data assembled in one location, it is expensive to move. And so it is much easier to move the computation to where the data is, run it there, and accrete over time more and more derivative data. And so over time, you can think of this gravity effect getting stronger and stronger over time, modulo maybe storage density, right? So if storage density improves, here I mean storage density of storage media. So if hard drives get better, if other kinds of storage media improves, then it gets easier to move things. At the same time, we're generating data at an exponential rate. So you have two exponentials meeting. One is the density cost reduction, and the other is the generation of data, and the generation of data is outpacing that cost reduction. So this means that over time, data will continue accumulating in locations and increase the gravity. So that means once you move large amounts of data in one location, you want to move your computation there and run it. So in IPFS networks and in Filecoin networks, you want to be able to do this very effectively and efficiently. We designed the Filecoin incentive structure to bring on a lot of hardware for computation itself. So lots of GPUs and lots of other computational machinery to be able to then run those pipelines on top of the data that's being assembled. So we first started talking about compute over data about 2 years ago, talking about, okay, great, like now that we've gotten this large storage platform and starting to onboard a lot of data, let's start building the primitives to enable that computation to happen in this environment. And since then, I think like the things that I'm most excited about is just seeing the breadth of projects that are emerging in the entire space. In particular, Bacalhau enabling all of these shared primitives that a lot of people can build on is like really, really exciting. And we sort of are seeing the kind of emergence of a number of different networks that are occupying different parts of a large design space to bring that kind of computation over this platform. So I don't know if that answers the question, but.
Absolutely. you mentioned Bacalhau in there, and I know they were, congratulations on hitting 1.0 today and having insulated edge compute jobs being able to run on Bacalhau. It's super exciting. Talk to us a little bit about the motivation to start the Bacalhau project and kind of where that insight of like, hey, there's a need for this to exist kind of came from.
Yeah, so when you think about computer over data networks, there's a lot of different use cases that mean that you need to tune some part of the infrastructure and the design of a network and the design of the software and the product space for those use cases. But there's an enormous amount that is common across those use cases that it involves very large-scale problem solving. And there were two kind of major gaps from prior compute runtime environments that weren't kind of solved well. One is, what happens when you're trying to do scheduling of jobs in a decentralized setting where you can't actually trust all of the other machines that you're interacting with, and you have to model and reason about deploying the jobs to nodes that may not be trusted. And so this means you need an infrastructure where you can define the job specs and so on in an environment where the job itself or the computer you're going to be running on is potentially untrusted. And so that's like one vector, is like how do you enable decentralized modes of computation, or how do you make the kind of access controls and access pattern part of the definition of the platform itself. And the other is just scalability in a kind of fluid way to just many different data centers around the world and to millions of nodes. And so when you think about things like prior large-scale compute runtimes, so things like Kubernetes and predecessors of that, kind of like Borg inside Google and many other type of large-scale computational job processing systems. All of them were kind of tuned for operating within a single data center and then running separate instances in other data centers. And that's kind of the thing that fit those workloads. But when you start looking at it from the perspective of building large-scale networks that are supposed to kind of bring together compute runtimes across those systems, you end up wanting a different type of primitive. You want to be able to kind of think about job scheduling at a different layer of abstraction than a particular cluster running kind of a number of jobs just within that region within a single trust domain. So this means you have to map many trust domains and you have to reach a different level of scalability. So we wanted to enable a lot of compute over data networks to emerge and find the different spots in that design space, but hopefully save a lot of time and effort in building each one of these by taking a lot of the common parts and building them as one protocol. So this is kind of similar to the kind of the progression of IPFS and Filecoin itself, where IPFS created a model for addressing and moving data, and then Filecoin created a way to hire a number of parties within the network to store your data. I sort of think of Bacalhau as that, creating an addressing scheme and a description scheme for these jobs, these decentralized compute jobs, independent of the trust environment they're going to run in or the trust, how much you should trust the users that are submitting things. And this gives you a really flexible environment on which to build many new other kinds of things.
So you mentioned a couple of times in there that you really believe that there can be many different successful compute over data algorithms and networks out there. And maybe talk to us a little bit about Juan's triangle, this intersection of verification, performance, and privacy, and how you see that impacting the types of different compute over networks that will exist, and why you think there will be many different compute over data networks that are maybe optimizing for different points in that triangle. And a visual is worth 1,000 words. I probably messed up one of the names of these things, so.
Let's see, I don't know if we can we get a projection through? There we go, awesome. So I sort of like first realized this, I think a couple of years ago, maybe a little bit longer. where there's like these really hard trade-offs when you think about decentralized compute networks. So this does not apply to centralized compute networks where you are living within the same trust domain and where privacy and verifiability are achieved primarily through a brand, through establishing a brand. And you basically get to run at the height of performance, and you spend no computational cycles on verifiability and privacy. So in decentralized networks, when you are trying to run things in some other untrusted domain, and you're trying to use cryptography to verify the computation, or you're trying to use cryptography to establish some privacy over the computation, you end up paying for that verifiability or privacy with huge performance cuts. So this means, so famously, fully homomorphic encryption would add like many orders of magnitude of a blow up to any computation, right? So 15 years ago, it was sort of seen as like intractable and impractical to even consider the idea of doing any kind of serious operation under fully homomorphic encryption, because it would just kind of take up what would be a few cycles in a CPU into kind of hours or months of compute time, depending on kind of what you're trying to do. So that exponential blow up was kind of insane at the time. And at that 15 years ago, it was sort of described, well, FHE is 20 years away. So funny story, time passes. We're now 15 years into that. Fully homomorphic, that's actually pretty prescient. Fully homomorphic encryption is basically here now. People are starting to use it. And it's predicted that both the tools and systems have improved, and the cost now is viable. So in the next 2 to 3 years, we'll start seeing the first large compute jobs using fully homomorphic encryption. But that doesn't get rid of the cost. You still have to pay this massive cost for that kind of full privacy. And fully homomorphic encryption does not on its own give you verifiability. So you still have to trust that the computation was done correctly. If you want verifiability, you have to run an additional protocol on top and pay an additional blowup. So whenever you move towards verifiability, you might be making it much harder to achieve privacy in some settings, and you have to pay an additional performance cost. So this landscape, you end up with very different points in this design space when you think about like zero-knowledge proofs or multi-party computation or trusted execution environments like SGX and so on. These are different points in a very large and rich design space that yield very different approaches to privacy and very different approaches to verifiability. And because of that, because you pay fundamentally different performance hits, and the kinds of computations that you can run in hardware are different, or in software are different, you end up with very different use cases willing to pay those kinds of costs. So you don't have like a nice, smooth surface where you can just kind of like run everything in one kind of architecture. You instead end up with many different software and hardware architectures that are tuned for different use cases. Why different use cases? Because only specific use cases will care about something so much that they're willing to pay like a 3 order of magnitude or 5 order of magnitude performance hit. Like in some settings, that is so valuable and so important that parties are willing to do that. So a good example of this is like, think about like gas costs in blockchains today. People are willing to pay vast amounts of money for adding a few numbers or making sure a ledger is consistent because it's so important to have that verifiability in the large scale network. Think about privacy. Being able to run some of these computations in a privacy setting matters that much. So because of these different approaches, you're very likely to end up with different architectures, different use cases. Those different use cases will appear to different customers, and those different customers will have different values and different brands. And so you end up with a very large design space with very fundamentally different islands in this environment, where over time you might have different networks starting. And as they grow, maybe, and as things get better and as computational hardware vastly improves, maybe eventually some of those might merge. Or when, say, compiler tooling gets so good that all of those sub-networks can be abstracted away, maybe eventually we might be able to kind of bring those kind of together under the same language. And so this might follow a similar progression to, to AI and ML software and hardware, where sometimes you can get certain software layers on top, being able to pull many different kinds of algorithms and many different kinds of accelerated hardware into the same environment, but that requires an enormous amount of kind of software infrastructure to enable that. And at the end of the day, in the lower layers, you are running on different kinds of environment. So this is kind of the claim here that at least in decentralized computation environments, when you want to have verifiability or privacy, you end up in different points in a very large design space, and you have these hard trade-offs that you have to decide between. So because of that, and this is kind of like what I was describing before around Bacalhau, you can think of building a lot of different common system tools, pulling those all together into a project, and then enabling a lot of decentralized compute network specific tooling to be built on top of that. And so that's kind of one of the goals. And so you might end up with something that looks kind of like this, where you have a network that has an enormous amount of data, because data has gravity, pulling together and aggregating vast amounts of data. And then you can bring your computational network into that environment to run it. And then so hopefully things like Bacalhau can enable computational network designers and developers to build, to start off with a lot of primitives already there, and kind of tune the network for the specific verifiability or privacy setting they're going after, and tune the use cases for, and tune the network and the branding and so on for that particular use case. One of the cool, so I don't know, that's a long answer, but.
Well, you had Filecoin at the base layer of some of these L2s. Talk to me about why Filecoin's a great home for these compute over data networks. What's going to cause a number of these L2s to harness, build on top of, utilize some of the tools or capabilities or market forces within Filecoin?
So I think, there's a few parts of this. One is just the hardware involved. So Filecoin has an enormous amount of hardware that is there and ready to process all of this. So the Filecoin network has about 13 exabytes of capacity. So like that's raw storage. It's getting close to 1 exabyte of data use. So we've gone from like 0 exabytes to 1 exabyte or close to 1 exabyte in about a year and a bit. So that, pretty fast kind of onboarding of a lot of data, and that's accelerating. So that's accumulating a huge amount of data to then run computations on. A lot of that data is public data. So this means large-scale public data sets with good licensing that enables you to then run computations on top of that. And because a lot of the storage providers already have tons of GPUs, you can run a lot of the types of computations that you might want to run over that data. So you can, it's sort of tuned for, it's a good substrate to do ML on. And a lot of the hardware requirements of the Filecoin network are pretty significant because we need to do these zero-knowledge proofs on the storage. But it's a very spiky workload where you need a lot of GPUs for a small period of time. And so there's a lot of, you kind of need burst capacity. And so the storage providers have to get a lot of these GPUs. But then there's a lot of time where those GPUs are not being used in that moment. So that's perfect for being able to use those for the computation. So this, so the claim here is that this might yield super cheap computational, a super cheap computational environment. Plus, you already have the data there. So and as you're kind of computing on that data, you're generating additional data that you can store in the same exact place. And so over time, this flywheel can keep going, right? So you generate more data, you run computations on it, you generate more data, you run more computations on it. And because of the kind of decentralized primitives for public data sets and with kind of proper, or not necessarily even for public ones, even for private ones where you have the correct access controls, if you have the right capabilities to run certain jobs, you can run the specific computations there and have a larger environment where it's not just one entity running computations over their copy of the data, but is instead large communities of participants. Many organizations can use the same data sets and the same sources of information to then generate all kinds of derived data sets and together create this large-scale data commons that in some cases is just all public data. In other cases, it's private data that's maybe permissioned for specific kinds of access. So think of scientific data sets where you might want to still encrypt them for certain privacy reasons, and then you want to run some computation where you're decrypting some parts and running computation over that. Or if you really need to, you can run some of these things in zero knowledge or full FHE or something like that.
Awesome. I'm curious, kind of we see many different L2s in this picture. How do an ecosystem of compute over data chains, like, operating in the same sort of environment, building on similar building blocks, how does that enable them to work together, build on each other, harness each other's strengths and capabilities, and actually make for a collaborative, like self-reinforcing ecosystem versus like a more competitive or like, one player trying to win the system? Like, what does Filecoin bring to that system?
Yeah, so I think so this sort of talks, like, if you think of that design space as creating different niches, people might, like different groups might compete in those niches, but across niches, you want, it's highly collaborative. And what you want is an environment where you can describe the data, and then you can describe computations that might transform that data and yield other versions of that data. And this might include kind of preparing things to be run in a particular other environment, right? So you can think of wiring the computation across these different computational networks using the same kind of job specs. So because of Bacalhau and the Bacalhau project and the kind of open source tooling that's kind of defined across many different computational networks, you can start describing all of these jobs in these different runtimes and couple them together. So you could have pipelines and computational networks that kind of cross between each other. One really important advantage to this, or one of the things that really enables this, is the using the blockchain setting for this kind of coupling of systems. So coupling these systems in single trust domains where you can't guarantee that the same computation is going to continue, or the same layout of the services is gonna persist, is kind of a harder setting. Blockchains give you this environment where once you ship a certain version of things, they tend to stick around and be hard to change, or you can always kind of fork them and keep them. And so you can create like more and more complex versions of these runtime environments that kind of accrete functionality over time. So that's one of the things that I think is useful. There's a whole other swath of kind of solutions to a bunch of these problems that we can kind of solve in common parts and common ways to kind of enable kind of cross collaboration of this. I think the biggest one though will be just the data cost. The data cost and the hardware cost. Solving that alone is just an enormous leg up into enabling communication and collaboration across those boundaries is really big. This is only going to get more like, only going to become more true as we start kind of requiring and demanding that our computation happens over like privacy preserving systems and hardware that actually tunes for privacy. So just to like kind of reinforce this point, I already covered it a few times, but like today the cloud environment runs with this like veneer of security where we've put a lot of emphasis on securing the kind of transport, and the entire security community spent a few decades like stressing a ton about how do you go from like a trusted domain and you send messages and communicate through like the dangerous internet into another trust domain. And many things, including the Snowden leaks, showed that like that's all well and good, but all you have to do is like decrypt over here and like steal all the traffic, right? And like that doesn't just go for security agencies. That happens in all kinds of environments and problems. And it yields this environment where only like 2 or 3 companies can actually solve all of the problems related to actually storing data safely enough for users and whatnot. And so it tends to create this like hyper-centralized environment. But again, like this is kind of like the veneer of security and the veneer of safety. You don't actually have strong cryptographic guarantees that your data is actually safe or the computation running over it is privacy preserving in any way. And so for the kind of people that are worried about the future in a computational environment where it is possible not just for nation states, but small corporations or even individuals to maintain models of every human on Earth and what they might do, like that's kind of like a weird, sketchy environment, and it'd be really great to kind of encrypt a lot of the information and data that we have around the world ahead of that. This is like the Cambridge Analytica stuff is like an example of like kind of a version of an attack that can be run kind of in larger scales. So I sort of predict that as soon as FHE gets significantly cheaper, maybe like 8 years from now, it'll be good enough, like governments are going to start requiring that certain kinds of computation happen in this FHE setting. At least the governments like really care about privacy. Some other governments may not. They might not want that computation to arrive there. And so I think like once you kind of get hardware in the picture, or for trusted execution environment type of stuff, or you get these computational runtimes happening, like FHE and whatnot, you end up in an environment where it is only like even more important that like you have large amounts of hardware and large amounts of data in one environment.
So I know we have a number of groups in the audience who are building their own decentralized compute over data networks. I'm curious what advice you would have as someone who has built significant distributed networks from 0 to 60 for them as they're getting started. What are some important things to focus on? What are some building blocks they can harness? What advice do you have for them?
So a lot of thoughts here. So one is one is kind of the basic thing about building any product in any system, which is kind of really guide your experimentation in an MVP-oriented way, where like you're really building a minimum viable product and shipping out to a community and getting going, tuning for the use cases that you think are valuable, and iterating and scaling from there. I just see so many engineering and product teams get stuck building for a very for like an idealized audience setting, and then the demands of the user bases kind of are in a different place. And so co-developing the thing with communities is really, really key. Then I would say there are important fundamentals that will matter a lot. So there's a bunch of decisions that you'll have to sweat at the beginning. But which ones those are is kind of unpredictable. Looking back through Filecoin and IPFS, there are a number of things where I worried about getting certain details right, and I was correct about that. And there are many that I worried about that were not actually that important. And there were things that I didn't worry about that turned out to be like really important. And so that's kind of like hard to predict. Like at least this should kind of give you some confidence that it's okay to build an environment where you can change things, and it makes it easier to kind of not get it right the first time. So things like self-description and things like agility to be able to improve systems over time is, I think, really, really key. So as you build those systems, like factor that in. Really find a very large-scale transactional throughput, meaning some problem space where there's a lot of groups that care about running those kinds of computations and are willing to pay large amounts of money for running those computations, and tune and design your software for those kinds of computations. Because at the end of the day, building any one of these computational networks will require an enormous amount of development and product time. So you need to kind of build that in a sustainable way, pulling in capital from the users that are trying to use this thing, right? So really tune your computational runtime for something that that a lot of people really care about. This is a long-winded way of saying, like the YC phrase of make something people want. Like people actually have to want the thing, and so tuning for that market space really matters. Then I would say just building open source. Like not every group can do this, but open source is just a phenomenal place to, a phenomenal way of building software and building systems where you get like this super linear advantage on anything that you build by building it with larger communities. I think not all compute networks here involve blockchains or crypto in some way. This kind of like probably like half and half and so on. But just consider whether that's useful or valuable to your compute network and whether that would be interesting. It can give you this like super powerful advantage to bring in massive amounts of computation into a network. So the really amazing thing about these networks is that you have really large-scale open markets that reduce friction of usage, so you can scale really quickly with some kind of new things can blow up like really quickly. I would say like think about the product evolution of your computational network, like what use cases are easier to get to first, but give you the right ordering to go after larger and larger markets. And so think about kind of like using gravity assists from smaller markets into larger and larger markets, and make sure that in each one of those you're delivering really high quality user experience. At the end of the day, you have to like build a super high quality project. And this is true for any engineering project, like lazy load, large effort things. So if something is going to take a lot of effort, really figure out when do you really need to do it and push that out, because you will have so many things to do that your entire engineering and development bandwidth will be saturated, and you don't want to take on huge amounts of effort initially if it's not going to be worth the cost in that point in time. So having kind of like, people tend to think about engineering time and the product development time as like a fixed quantity, or like a stock problem. It's really a bandwidth problem. You have a certain amount of hours, and if you solve the more like the problems that matter to the community now, to the users now, you'll get like this self-reinforcing structure, which will give you more bandwidth. And so like really focus on that. I just see so many groups that get that off. And think one other thing is like there are large communities that care about building these things. So really find groups that might support you. So I'll give an example. I think a number of folks are probably starting companies, and so this. Let's see. So this is kind of a diagram that I've used recently, and like you can think of any starting a startup kind of thing and plot it in this environment, but really kind of understanding where you. This is of course before you actually have like a larger. This kind of like seed and before, and so when you're starting something new and from scratch. Think of this kind of staircase of funding or staircase of help. And there's lots of different programs for each of these stages. One interesting observation here is like going from experimenting with ideas to actually starting a startup and getting kind of accelerator scale funding, like small amounts of funding. That part has a huge gap in the market. There isn't that much support there. That's like a part where lots of projects go to die. And so like just kind of understanding where there are systems and programs that can help you develop, and where there aren't can kind of help you plot this space. And so think about kind of moving throughout these stages as you find like a solid thing. And there's lots of different kinds of grants and prizes and scholarships and whatnot that can help parties in those early stages. And then after that, you get into like accelerators and angels, and then VC, and so on. And so having a good understanding of the capital landscape to be able to fund your projects is really key. And so this is kind of startup private funding. There's also environments with large-scale public funding. That's also pretty interesting. You can think of a similar kind of structure. That one looks even spottier. Like this is a pretty well-defined low effort jump at each step. But like the public funding market is just dramatically steeper. Like you go from like a lot of tiny little bits of funding, and then like a huge cliff, and then maybe you might be able to jump over. But yeah, so kind of like leverage the programs that are out there for you.
Awesome. I want to make sure that everyone can go to lunch. So maybe last question, but also revving back to the title we'd at least initially given people for our talk. What interesting lessons, technical lessons, human lessons, strategic lessons would you share from having built a massive decentralized storage network for folks that are now going and building distributed compute over data networks? Like, what are some of the insights about the architecture, the development, the evolution of Filecoin that others might learn from, harness, things that were surprising, things that you look back on with like 2020 hindsight and you're like, oh, we would have done that differently, or thank goodness we did that thing because that really set us up for success.
Yeah, I mean, so that's like a large list to enumerate, but I'll maybe highlight some things that just come to mind. And here, like, my answer will probably be biased by what was different as opposed to what we did really right. And when you do something right and the world sort of recognizes that, you don't get a lot of noise about it. It just sort of works, and then you move on to the next thing. So you can get tons of things right and not notice it because like just things are working as intended. So things that are like more salient are where you suddenly had to like struggle with a thing and then kind of change it. There's a lot of lessons here, but I think like the most important result in the crypto economy is the Bitcoin block reward, and that's like the most not well understood. It's kind of like a very simple mechanism, and it is tremendously powerful. Right, so we're talking about the combination of two mechanisms. One is the ability to move payments, and the other to having an economic release of value coupled with a verifiable way of proving a certain amount of power, like auctioning off a certain amount of currency for like proportional amounts of power contributed, gives you this like tremendously powerful incentive structure that has caused one of like the largest energy consuming systems on the planet. It's a shame that all of that is wasted work and like kind of really bad, huge waste. It'd be great to like use that for useful versions of work. But I think like that is one of the kind of where a lot of this entire world started, and is one of the most, again, misunderstood and misappreciated like components. And so I think understanding the economic behavior of that component is, I think, really, really key. And when I look back at like important challenging environments, challenging things, it comes from like people not fully grokking that, at least in kind of in Filecoin. At the same time, the massive, like a lot of Filecoin success is attributed just to that. When you think about the massive scale computational hardware that the Filecoin network has been able to achieve, it just comes from that, from getting a lot of those pieces right. Maybe some other kind of design lessons. I think Filecoin became way too complicated because we didn't layer it well enough, meaning IPFS is much more layered, and so that ended up more successful. For Filecoin, we ended up kind of coupling too many mechanisms together, and it ended up making the system harder to change. So one important lesson here is really learn well from good well abstracted layered designs and make sure you get that right. Initially, a lot of people will complain that there's way too many layers and way too many abstractions, and that'll be constantly a tension. But if you kind of have an environment where it becomes easier and easier to abstract things, that can be like a good setting. In most cases, once you have abstractions, people start depending on them and they become really hard to change. And so making sure that you have good layering initially can be extremely critical. I think being able to, like self-description is one of these things where to this day I still have to like convince people about. It's one of the kind of most useful, one of the most like useful ideas across Filecoin and IPFS was just the very basic idea that when you define formats or when you define systems, you should self-describe them. You should include data in the format itself to describe the format that you're using. And this gives you an enormous amount of agility and ease of changing large-scale systems. This has probably saved thousands of I don't know, like thousands of years maybe of like engineering time and development time in a lot of systems out there by being able to kind of smoothly upgrade systems. I think just so many groups end up like building hard to change single things, and it becomes difficult to evolve them over time. I don't know if there were some specific things that you were thinking about.
Nope. If we have space or if anyone wants to hang out, we're happy to take questions. Otherwise, I'm also happy to let people go off and eat some lunch. Maybe we'll take one or two questions if there are some. Okay. Shout your question and I'll repeat it.
You brought up fully homomorphic encryption and that might be mandated by governments to be used, like in 8 years or whatever, to achieve, robust privacy. And then you alluded to the possibility that quite the opposite could happen, and that the governments could very much ban this type of computation. What role do you see distributed ledger technologies in general, maybe Filecoin in particular, in, I guess, combating these kind of tyrannical regimes, basically?
Okay, just to repeat the question, it was long enough that I'm going to paraphrase. It's great. You might have governments that mandate fully homomorphic encryption. You might have governments that ban fully homomorphic encryption to make sure they have, transparent access to their citizens' data. What is the role of distributed ledger systems, Filecoin, others in kind of enabling access to privacy-preserving technologies?
Thanks for the prompt for me to give a second talk. This is one of those things where only a small fraction of the world, it's kind of like nuclear weapons or AGI risk or like, I don't know, supervolcano risk is so unlikely. But there's a bunch of risks, or like maybe engineered pandemics and so on. There are like these very high risks that are non-linear, where like if they start happening, they can happen extremely quickly. And because of how humanity works, only a very small fraction of people in the world end up spending a lot of time kind of understanding or kind of combating these kinds of problems. And so it's very kind of hard for humans to intuit how to operate with these kinds of like exponential risks, where things can like change very quickly. Think of how the whole world responded to the COVID pandemic, and how like many governments and systems just got completely taken by surprise, even though we've understood exponential growth and bio problems for a century and a half or so. So I think like in this particular case, the way that I kind of like think about this is that in the good case, this never becomes an issue, or it doesn't become a bigger issue than it is today, and everyone kind of just assumes that it was kind of like wasted time and effort and wasted time and work, and like it never happened, and see like all of those people worrying about this were like totally wrong. In the bad case, everything goes. A lot of people in a lot of locations in the world might encounter an extremely terrible living environment. Think of like the most oppressive regime that you can think of, and that you like think in history was like awful. Don't have to like go into specifics and kind of like argue the merits or whatever, but just think of like whatever you think is like a terrible, like the worst government that you know of, and that can happen again in the future. There's no reason why some of these environments couldn't fall into that. And a thing that's kind of like very different is that the kind of computational infrastructure that we've built today is so ridiculously powerful compared to what we've had in the past, that now it's not just large nation states that can run this kind of like complete and total surveillance of what people do. You can use a lot of like fragments of information that you can find on the web about things and train like pretty good models today to kind of predict what parties are doing. And so you end up in this like very different point in the design space where like not that powerful governments or corporations or groups can get like this crazy advantage over large groups of people if those environments aren't careful to like mitigate these risks. So I think a lot of people are kind of like much more aware of this like these days. And so I think there's a lot of like groups and in various governments that are like very legitimately like very concerned about this kind of stuff. Like for example, the killer bots are like a specific problem where they can take these like small quadcopters and put guns in them and so on. And many countries around the world like got ahead of this and kind of banned them, thanks in great part to like important work from some policy groups. But like that doesn't go for some of these other things around kind of like population control systems and credit systems and things like that, where they're actually being tried, found to be successful, and actually starting to get exported to other countries. And so this is like very pernicious because this is like not a very obvious threat, and it can very quickly slide into like a bad setting. So I think we have a good point in time right now where like you can fight a lot of this by forcing the computational environment to drastically improve and bake in like our current present-day notion of human rights into the computational platform. So think of the computational platform that you use today. Ideally, you should be able to kind of bake in important freedoms that we think are critical today into those platforms and make it extremely difficult to shift out of that equilibrium. If we can lock in that equilibrium, it'll be very difficult for certain kind of future attackers. And so today we have a lot of like pretty good jurisdictions that care about establishing that level of security. So I do think that many governments will actually mandate a move towards some of this. We are seeing significant improvement in this in some places. The trouble is like this tension between like safety and security inside of a jurisdiction against like kind of like external attackers or whatever, versus kind of like safety and security from the future. Meaning it's like kind of a weird thing. You're trying to establish a security perimeter against like future attackers that might take control of the jurisdiction. And so that's kind of like a weird environment to be in. However, there are lots of governments and policy groups and builders and whatnot that understand this problem space really well and can like tune for that. And it's not any particular country. Like you can map any groups, like you can map all the different countries around the world, and like they're in different parts of the design space. And so I do think that like we have this good time still where you can lock in a lot of these pieces, and then hopefully all of this we'll have seen as like a problem that like never, nothing ever happened, nothing bad ever happened. It was all like good, and this maybe was wasted work. And so like that's the good case. And so I think we have some period of time where we can achieve that.
Awesome. Yeah, we can get additional entire talks out of well-placed questions. I'm happy to take one more, and then I want everyone to go get food, if there is one. Otherwise, we can go get food right now. All right, let's go get food. Thank you all.